The first example, a sinusoidal wave of the wavelength equal to the 1 meter. So let me take a note first. We have the wavelength equal to the 1.0 meter, and then the amplitude, right, equal to the 1.5 meter. Is traveling with the speed of the 0.5 meter per second. So we have to v equal to 0.50 meter per second. So then at the times equal to the 0, the particle on the wave is at the x equal to the 0 and y equal to the 1.5 meter. So so this is the initial conditions of the particle on the wave. So now compute the following quantities. Okay, so now for the frequency f, right? We know the v and we know the lambda. We can find the f using the v equal to the f and then times the lambda. So then here we have that the f equal to the v and then over the lambda equal to v just equal to the 0.50 and the lambda equal to the 1.0. Then we can get the f equal to the 0.50 hertz. So that's going to be the frequency. Okay. Now for the part B, we want to find the period t of the oscillation. So now we know the frequency, we can find the period, right? We can use the t equal to the 1 and then over the f equal to the 1 and then over the frequency is 0.50 and then just equal to the 2.0 second for the period of the oscillations. Now for the part C, okay, for the wave vector k, right, k equal to the 2 pi and then over the lambda. Okay, because we know the lambda already, then we can use this equation to solve for the k. The k equal to the 2 pi over the lambda, just equal to the 2 pi and then the lambda is equal to what? Equal to the 1.0, right? Then finally we can get the k equal to the 2.0 times the pi. It's going to have unit as the radian per meter. Okay. Part D, the angular frequency. Okay, we know the frequency f and we know the times t, right? Actually we can use the omega equal to the 2 pi and then times the frequency to solve for this one, equal to the 2 pi and then the frequency is equal to the 0.5 hertz. So we have 0.50 hertz, right? Then okay, it's going to be equal to the 1.0 times the pi, radian per second for the angular frequency. And then actually we can use this equation to solve for the angular frequency as well, because we know the k already and we also know the v already, right? Okay, so let's try this one. Omega equal to the k times the v. Okay, let's try this. So we said that the omega, right, equal to the k and then times the v. The k is 2.0 times the pi. And now for the v, right, for the v is 0.5 meter per second. Then just equal to the 1.0 times the pi, radian per second, just the same answer as the previous one, right? So now finally for the initial phase, right, phi. Okay, so as I just mentioned before, right, if we just want to solve for the phi, then we need to know the initial conditions. Okay, we need to know the initial condition to solve for the phi here, but we know it already. So it said that when the terms equal to the 0, right, x equal to the 0 and the y equal to the 1.5 meter. Okay, so we know that when the terms equal to the 0, x equal to the 0 and the y equal to the 1.5 meter. Okay, so let's use this one, y equal to the a and then times the sine of the kx minus omega t and then plus the phi. Okay, let's use this. Now let's sub everything into the equation. Y equal to the 1.5 equal to the a. The a is what? The a is the 1.5 as well. Okay, and then times the sine of the, okay, so now the kx, right, x equal to the 0 and the terms is equal to the 0 as well, and then plus the phi. So you can see that 1.5 and 1.5 just cancel out, and here we have only the sine of the phi, right? Then you can get that the sine of the phi is equal to 1, or we can say that the phi is equal to 1. Okay, sine of what equal to 1 is to be equal to the 90 degree, right? Then we can get the phi equal to the pi over 2. So let me just use it as the radian here. Okay, okay, now another examples. Let's consider this. The wave function for a traveling wave, right, on a tau string. So tau string just means that the tension is quite high. Okay, I mean the string is not loose. So is equal to this one. So this one is in the SI unit. It means that unit of this one must be meter, and units of the 10 pi, right, is the radian per meter, and sorry, the radian per second, and this must be radian per meter. Okay, so now for the part A, what are the speed and direction of the propagation of the wave? Okay, so let's talk about the direction of the propagation first. Okay, if we look at this question, right, so as I just mentioned before, right, I said that if the sine in front of the kx and omega t are the same, so it means that it is the positive side. So it means that the wave will travel to the negative x direction. But now if the signs in front of the kx and omega t are different, in this case it is the negative side, right? So it means that the waves will travel to the positive x direction. Okay, so now in this case, okay, we have this is omega t, right, and this one is the kx. So the sign in front of the omega t and the kx are different, so it means that the wave will travel to the positive x direction, right? Just travel to the positive x direction. Okay, that's going to be one thing. Now we just want to find the speed of the wave. Okay, so let's look here. We have the 10 pi times the t. Okay, so remember that the variables in front of the t is what? Is the omega, right? So we have the omega equal to the 10 pi in the unit of the radian per second, and also the variable in front of the x, right, it's just equal to the 3 pi. So we have the k equal to the 3 times the pi radian per meter. But now we just want to find the speed of the wave. Okay, so then we can use this equation, right? The k equal to the omega over v. So it means that the v here equal to the omega and then over the k. Okay, so we can get that the v equal to the omega and then over the k equal to, okay, so we have the 10 pi and then over the 3 pi, right? So it's going to be equal to the 3.23 meter per second. So this is the speed of the wave, of the traveling wave. Okay, so now for the part B. What is the vertical displacement of an element of the string, right? At the terms equal to this and the x equal to this. Okay, so we just want to find the vertical displacement. So it means that we just want to find the y, okay, at these terms and this position x. Okay, so that's quite easy. We can just plug in everything into this equation. So we have the y equal to, okay, we have the 0.350, right? And then times the sine of the, okay, so we have the 10 times the pi and then times the t, which is equal to the 0, and then minus the 3 times the pi, right? And then times the x. The x is 0.100 meter. Okay, and then plus the pi over the 4. Okay, so then we can just use the calculator, right, and solve. It's going to be equal to the this one, right? So it's just equal to negative the 5.48 times 10 to the negative 2 meter. Okay, part C and the part D, right? Okay, let's just start from part C first. We just want to find the wavelength. Okay, we just want to find the wavelength. So now we know the k, right? We know the k. Then we can find the wavelength. We can say that, okay, the k equal to the 2 pi and then over the lambda. Then we can get that the lambda equal to the 2 pi and then over the k. The k is what? The k is the 3 pi. Okay. Then we can get the lambda equal to the 0.667 meter. So this is the wavelength lambda. Now for the part D. Okay, for the part D, omega equal to the 2 pi times the frequency. Okay, 2 pi times the frequency, and then the frequency is equal to the omega and then over the 2 pi equal to, okay, omega is 10 pi and then over the 2 pi, so it's just equal to the 5.00 hertz for the frequency. Okay, so now for the part E, what is the maximum transverse speed of an element on the string, right? Okay, so what does this mean? Okay, so if we look at this simulation, right, and then if we follow the path of the red dot here, you can see that the red dot, right, we have the speed equal to the 0 at the maximum and this minimum position, right? But then the speed of these elements, right, of the red dot, will be the maximum when it is at the equilibrium position, which is the y equal to the 0. Okay, so don't forget that the element, right, or the particle on the string, right, it just moves as the simple harmonic motions. And from the previous chapter, we said that the speed will be maximum at the equilibrium position, which is the y equal to the 0. So in this case, in this case, we can get that, okay, the Vmax, right, the Vmax of the elements on the string is going to be equal to the omega and then times the amplitude A. Okay, this question, if you remember, right, from the previous chapter, equal to, okay, so now the omega is just the 5.00, and now for the amplitude A, right, it's just 0.350. Okay, so don't forget that this one is the amplitude. Oh, sorry, no, the omega is 10 pi, sorry, my bad. Omega is 10 pi, and for the A is the 0.350. Okay, so now we can just use the calculator and to solve that. The Vmax, right, is equal to the 11.0 meter per second. So this is the answers. Oops. Okay, so now before we just moving on to the next topic here, right, the superposition of the two towering waves, which is this one. Okay, so there's some details that you need to know about the wave on the string, and then about the traveling wave as well. So let's consider this. Actually, we can find the speed of the wave on the string. Okay, we can find the speed of the wave on a string. So I'm going to give you this question without any proof. Okay, so just use this question. So let's say that if I have a string, right, so if I have the string here, and then I'm just grab the string on this side, okay, and then let's say that the tension on the string, right, is just equal to the Ft. Okay, so let me just draw the field diagram of the string here. We have the tension on the string equal to the Ft. So then if the length of the whole string equal to the L, okay, so the length of the whole string equal to the L, and also the mass of the whole string is equal to the M. Okay, so then if I just disturb the string a little bit, okay, so I just want to make the pulse here, then we're gonna have the pulse, and then the pulse is traveling to the right hand side with the speed of v. Okay, so now we just want to find the speed of this pulse on the string, right, as function of the Ft, M, and then the L. Okay, so then the equation is here. We can get that the V equal to the square root of the tension, the Ft, and then over the mu. So what is the mu? The mu is equal to the mass of the whole string, right, and then over the length of the whole string here, right, equal to the L. Okay, so the mu is called the linear mass density of the string. Okay, the linear mass density of the string. And that's it. Okay, so then this will be the speed of the wave on the string. But one thing that you need to keep in mind is that this equation is going to work if and only if the v is much greater than the vy. So you remember the Vy, right? What is the Vy? The Vy is going to be the velocity of the element, right, on the string. Okay, it's just oscillating up and down here. Don't forget that. But now for this V, right, it's going to be the speed of the wave that's traveling to the right hand side. Okay, so this equation is going to work if and only if the V is much greater than the Vy. Okay, then it means that if we know the tension on the string, right, and if we know the linear mass density on the string, we can use this equation to find the speed of the wave on the string as well. Okay. The other details that we need to talk. Okay. So if we look at this simulation again, right, you can see that the wave will travel to the right hand side, but then the elements of the particle on the string, right, it's just oscillating up and down. So then the question is, which type of the physical quantities that the wave carrying as propagating or traveling? Okay, so now you can see that as the wave is traveling to the right hand side, it doesn't carry the elements of the string anymore, right? Because the element of the string, right, it's just oscillating up and down. Okay, it just stay at its position x, right? And if you have the displacement to be the y. Okay, but then what does the wave carry as propagating? So actually you may guess that, right, the wave will carry the energy as propagating. So it means that as the wave traveling to from the left and then to the right in this picture, right, it's gonna carry the energy and to the right hand side as well. Okay, so now we just want to show this. Okay, we just want to show this. Okay, so let's say that we just want to show that. Okay, to show that the wave, right, will carries the energy as propagating. Okay, so let's consider an element on the string. So let me just make the copy here. Okay, so let's see that if we just look, okay, let me just make to be, yep, this one. Okay, so if we look at the particle on the string, right, let's say this one, let's say this particle. Okay, so let's say that the mass of this particle, right, is just equal to the dm. Okay, just equal to the dm. And don't forget that this particle, right, is oscillating up and down with the velocity equal to the Vy, right? It's just equal to the Vy here. Okay, so now you can see that the kinetic energy of the particle of the mass dm is, okay, the kinetic energy of the particle of the mass dm is, so let's say the dk. Okay, the dk, because right now we're talking about the dm here, right? So let's use the kinetic energy as the dk. The dk equal to the 1/2 mv squared, right? But now this mv have the dm, and the v is going to be the Vy and then square. Okay. So now let's just plug in the Vy into these equations. Okay, so it's the Vy. Then looking again, right? The Vy is equal to negative omega A, and then the cosine blah blah blah. Okay, so let me just copy this one. Oops. Okay, so then we have the 1/2, right, and then the omega square times the a square, okay, because we have the Vy square, right, and then times the cosine square, and then blah 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 here. So this blah 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 is just equal to this argument, right, and then times the dm. Okay, but now I just want to convert the dm to be the mu and then the position. So how? Okay, so let's say that if the width, okay, if the width of this element equal to the dx, okay, if the width of this string element, right, just equal to the dx, and then we say that we have the mu, right, we have the mu equal to the mass over the length. So then if the mass of this element equal to the dm, and then the length of this element equal to the dx, right, so now you can see that we can just write down the dm in the terms of the mu and then the dx, right, which is equal to the mu and then times the dx. Okay, so now let me just rearrange the equation again to be the 1/2 omega square times the a square and then times the mu. Let me just put the mu in front of here. Oops. Okay, and then times the cosine square blah blah blah. Oh, sorry, and then times the dx as well. Okay, now let's find this. Okay, let's find this. The rate, okay, the rate of the change in kinetic energy, right, of the rate of the change in the kinetic energy of the particle of mass dm. Okay, so let's say that so if we just want to find the average, but okay, let me just write down first. So we say that the rate of the change in the kinetic energy of the particle, right? So the rate of in the physics, it just means that per time, okay? So in this case, we have the dk by the dt, okay? So it just equal to, again, we have the 1/2, and then we have the mu, right? And we have the omega square, and then times the a square, right? And we have the cosine square and blah blah blah, and then times the dx by dt. Okay, so now let's see this. What is the dx by dt? The dx by the dt, right, it just equal to the v. Okay, it's just equal to the v, which is the speed of the traveling. Okay, which is the speed of the traveling here. Okay, then if we need to find the average of this one, okay, if we just want to find the average of the dk by the dt, okay, so in this case you can see that this is just constant, right, and the v here is constant as well, but this one is not constant because that depends on the x and then on the t. Okay, so then what is the average of the cosine square? Okay, so I'm gonna script this this proof, but let me just put it this way. We can get that the average of the cosine square equal to the 1/2. Okay, it's just equal to the 1/2. This is the average of the cosine square, right? So then here we can get that is equal to the 1/4 times the mu, and then times the omega square times the a square, and then times the v here, right? Okay, times the v here. So then what can we conclude from this equation? So now you can see that it just depends on the v, right? The velocity of, the speed of the traveling. So what does it mean? In this case, it's going to be that, okay? So this term, right? This term here, it must be equal to the rate, okay, of the transfer in the energy, right? It must be equal to the transfer in the energy of the wave. That's it. Okay, so now we just show that the wave will transfer in the energy with the rate equal to this one. Okay.